example from homework, curve sketching and limits. And we're going to look at graphing this rational expression. So we're going to look at a few aspects of this. So looking at this, we're first of all going to factor this expression so we can see the factors in the numerator and factors in the denominator to figure out our restrictions and see if anything cancel out, and we can then establish holes and vertical asymptotes. And from the factors in the numerator, we can also establish zeros. So the first thing is, again, we're just going to factor. So factoring this, I end up with x minus 6, x minus 3, and then x minus 1. In the denominator, we have a negative 12, so we need to have a negative and a positive, so we end up with x minus 6 and x plus 2. Okay, so we can see that there are some factors that cancel. So these factors cancel, so there must be a hole at x equals 6. And it's useful to know the y coordinate of that hole. So I'm going to plug 6 into this expression. So I end up with 3 times 5 divided by 8. So y is equal to 3 times 5 is 15 divided by 8. Okay, so there's my hole. I also have a vertical asymptote as a restriction. So there's my vertical asymptote. So my vertical asymptote is going to be at x equals negative 2. Since it's in factored form, I should get my zeros. So the zeros of this expression are going to be at x equals 3 and x equals 1. And while I'm here, I might as well get a y-intercept. Plugging in 0, I get x equals 0, y equals positive 3 divided by positive 2. So the y-intercept is going to be at 3 over 2. So it's always useful to get some points. We don't want to just get a whole bunch of random points because it's becomes difficult to deal with. But if we need some coordinates, it's always good to, you can always plug in x's to get y coordinates. So I'm just going to put in a few things in here. So my zeros are going to be at 1 and 3. So 1 and 3, I have some zeros, looks like. I've got a y-intercept at maybe 1.5, somewhere around there. I have a vertical asymptote at negative 2. So at negative 2, I have this vertical asymptote that goes something like that. Okay, and I have a hole in the graph as well. So the next thing is I'm going to look at this expression. The numerator is 1 degree higher than the denominator. That means this has a slant asymptote. And a slant asymptote essentially is endpoint behaviors, just like a horizontal asymptote. So we want to know what's happening at the end, and to get the slant asymptote, we should do some long division. So I'm going to take that expression, so x plus 2, and that needs to divide into the numerator, which is x squared minus 4x plus 3. So it goes in there x so minus 6 so I have a remainder of 15. The remainder does tell us something about this. If it's positive, positive remainders go across this diagonal, negative remainders go across those diagonals. But that's not necessary because we have these coordinates anyways. So I'm going to draw in my graph here. Okay, so I'm just going to drawing my -6, somewhere around here, and it's got a slope of 1, so it's going to look something like this. Just extend my vertical asymptote there. So it looks like my graph's going to go through these points like that, and we're going to have some part down here. And if you want, you can get coordinates down here. We are going to have some coordinates from the derivative, but the location of this is largely going to, we're not going to be too picky about that. Okay, so I'm just going to get rid of that. Okay, so the next part then is we want to differentiate this to find our min and max points and do a slope chart. So I'm going to get the derivative. So first of all, I'm going to take a look at this original expression. So I want the derivative of x squared minus 4x plus 3 over x plus 2. And notice that I didn't keep the factors that I canceled because the shape of this graph is the same, and so the derivative of this graph versus the original graph is going to be exactly the same. So my derivative function is going to look like this. Y prime is going to be 2x plus 4 times x plus 2, and then minus x squared minus 4x plus 3, like that, and the denominator squared. Okay, so there's my derivative. I'm going to simplify this. So 2x squared plus 4x, so plus 8x plus 8 minus x squared plus 4x minus 3. Okay, so my derivative expression looks like this. X squared plus 12x plus 5. Oops, I think I made a mistake here. Sorry, this should have been minus 4 here. Okay, so that would make this 4x, so those are going to cancel out there. So 2x squared plus 4x minus 4x. Okay, so then it becomes minus 8 minus x squared plus 4x minus 3. So x squared plus 4x minus 11. Okay, so then I'm going to find where the derivative is equal to 0, so I'm going to solve the numerator. So this is not a factorable numerator, so I'm just going to plug it into the quadratic formula. So my solution for my derivative is going to be x is equal to negative 4 plus minus square root of 16 minus 4 times 1 times negative 11. So that's 16 plus 44. That's going to be 60. So I end up with negative 2 plus, or negative 4 plus minus square root 60 over 2. And that will simplify to negative 2 plus minus square root 15. Okay, and this is approximately equal to negative 5.9 and negative 1.9, approximately. Okay, so then we have established our zeros for this, our derivative. So I'm going to do a slope chart here. So I have my -2, -2, -2 root so -2 plus root 15 on this side. So that's positive. And then we're going to have -2 minus root 15 on this side. And here's our vertical asymptote, so that is an undefined value. We have 0 slopes here. We should test those slopes. So if I plug into my derivative function, f prime at, let's do -6. If I put -6 into here, it's 36 minus 24 minus 20 minus 11 is going to be positive. Okay, so we have positive slope going through here. And choosing some number in here, let's choose -3. When I plug -3 into here, I end up with negative. So it's going down. Choose a number between -2 and 1.2. So I'm going to use f prime at 0. Okay, f prime at 0 is going to be negative. So it's going to be going down through here. And choosing some number to the right of 1.2, 1.9. I'm going, and again, that's positive 1.9. So I'm going to plug in 2, and I end up with a positive slope. So it's going to look something like this. Okay, so I have, it looks like I'm going to have this portion here and this portion in here like that. Okay, so I'm just going to sketch those in. I just want to make sure I have the right x coordinates in here. So my 0 is going to be, or my bottom of my curve is going to be at about 1.9. The bottom of the curve here is at about negative 5.9, so somewhere maybe around here. Okay, so I have a max happening here. It's going to follow the asymptotes this way. It's going to follow the asymptotes here, my min, and then it's going to follow the asymptotes like that. Okay, so there's what my graph's going to look like. I had to do analysis on these points. I found a slant asymptote. I worked out the derivative equal to 0. I did a slope chart. There may be times where you're asked to plug these x coordinates in to find the y coordinate of these min and max. However, when you have complicated expressions like this to plug in awkward numbers, we probably will not require to do that.